Today, I am presenting on the optimal stopping problem of a Markov chain. Consider the following simple game example. A player rolls a die. If the roll is 1, 2, 3, 4, or 5, the player can end the game and pocket a payout that equals to the roll. If the roll is a 6, however, the game ends automatically and the player receives no payoff. This game can be represented by a discrete time Markov chain, where the outcome of each roll represents the outcome of the process at any given epoch. The state space I is given as such, and the transition probability matrix P is given as such, where every entry Pij represents the transition probability from any state I to any state j in the state space. Notice that the sixth state is an absorbing state. Therefore, P from 6 to 6 equals to 1, whereas the transition probability from 6 to any other state in the state space is 0. The process eventually has to end up at the absorbing state, and so the game cannot continue forever because the player has to roll a 6 at some point. We also define Wi to be the intrinsic value function, where it represents the payoff associated with stopping at a state I. The goal of the game is to find a strategy that maximizes the player's payoff, and this example represents an optimal stopping problem of a Markov chain. We now move on to the general statement of the problem. Let Yt be a discrete time Markov chain with state space I and stationary transition probabilities Pij. Let K be the absorbing state of the state space. Define W as the intrinsic value function, and let tau be any stopping rule that prescribe a time to stop the process. The goal is to find the stopping rule tau such that the conditional expected value of W at the stopping state y tau, given that the process starts at state I, is maximized. Now, we provide an overview of the solution. The key to solving this problem is to characterize the conditional expected value by way of a superharmonic function that dominates Wi at all state space. Here is a definition of a superharmonic function. If f is superharmonic, then the value associated with the starting state I is always greater than the value associated with any subsequent state j, averaging across the transition probabilities between I and any j's. So to finish our characterization, we need to introduce an auxiliary function called the maximum expected payout function f. M is defined to be the conditional expected payoff at any stopping state y tau, given that a process starts at I, maximized over all possible stopping rules tau. A little closer observation will reveal that M can be written as the following systems of equation called dynamic programming equations. Intuitively speaking, this is because when the process does not start at a stopping state, thinking back to the simple game example, the player would only choose to stop the game when the intrinsic value of the value they receive by stopping the process at that state exceeds their holding value, i.e., the payoff they could expect if they continue playing and continue sticking to the optimal strategy. We now introduce our central theorem. Our central theorem characterizes Mi of a dynamic system expressed as the dynamic programming equations as the smallest superharmonic function with respect to the transition probabilities of the Markov chain that dominates the intrinsic value function. To prove this, we actually need two auxiliary lemmas. The first lemma states that under any stopping rule tau, if f is a function that's strictly greater than w over the entire state space, then the conditional expected value of w at a stopping state y tau is less than or equal to the conditional expected value assigned to the stopping state by f. The second lemma states that if under any stopping rule, if f is superharmonic with respect to Pij, then the value of f given to the starting state I is always greater than equal to the conditional expected value of f at the stopping state y tau. i.e., the player will always be better off stopping the process at the starting state if the maximum expected payoff is superharmonic. Given these dilemma, we can show that if fi is any superharmonic function that dominates wi with respect to pij, fi has to be greater than or equal to mi, and therefore completing our proof of the theorem. With this powerful theorem, we are able to solve m, the maximum expected payoff function, by successive approximation. So we first define a superharmonic function f sub 0 as such. F sub 0 is superharmonic because no matter which subsequent state the process visits, the payoff f of that subsequent state can be no greater than f of the starting state. We then recursively define f sub n in such a manner, and please notice that f sub n is strictly decreasing. Notice that the sequence of f sub n is strictly decreasing, and f sub n is superharmonic with respect to pij for all n in natural numbers. We also notice that since the sequence f sub n is bounded below by wi, it has a limit, and we denote that limit to be f. An important fact is that the maximum expected value function m actually equals to that decreasing limit of the sequence of f sub n functions. So let us illustrate how this important fact can be used to derive a solution by revisiting our simple game example. We can define f sub 0 to be 0 for the absorbing state and 5 for any other state. Notationally, we are going to use u sub n to represent the f sub n associated with each state in a state space. So u sub 0 is as such. And using the definition of s sub n we have just enumerated in the previous slide, we find that u sub I is strictly less than or equal to u sub 0, u sub 2 is strictly less than or equal to u sub I, and after 10 iterations, we actually are getting pretty close to the limit. And if we keep calculating, we'll find that as n approaches infinity, we have the limit to be given as this vector. So this is the maximum expected payoff that we can expect given we start at each state in the state space. With the maximum expected payoff function, we can now talk about the optimal strategy, which is to keep rolling if the player rolls a 1 or 2, stop rolling if the player rolls a 4 or a 5. If the player rolls a 3, the intrinsic value at that state equals to the value of continuing the game and sticking to the optimal strategy. So both choices will be optimal at the third state. Thank you for listening.